Any statistical test you can do, I can hypothesize better. I can do anything significantly better than you. No, you can't. Yes, I can. No, you can't. Yes, I can. No, you can't. Yes, I can. Yes, I can. Yes, I can. And now you can too. You've made it to the end of the class. This is the last bit that you have to go through preparing for the final, and it's exciting. And the fun part is, if some of you have been thinking to yourself, hey, this wasn't so bad, this was fun, okay, consider this as a direction for you. Statistics can be a lot of fun. We get to play in everybody's backyard. You've seen examples with chemistry, with biology, medicine, we've had psychology, sociology. Whatever you're thinking on doing with your career, if you add more statistics, it will look good on your resume. Your employers will look at that and say, oh, this person knows how to think logically. They can tell what the data really means. They can do the analysis for us. Because a lot of the reason why people hate statistics is they're just scared of it. So I realize some of you out there are thinking, this is the only stat class I will ever take. That's fine. That's called job security for the rest of us. But if you thought to yourself that this was kind of fun and not so bad, come talk to me. We can figure out what might be a good fit for you. The next class after this would be Stat 3050. It covers ANOVA, some advanced regression. It goes through a whole array of topics designed to make it so that you could go into any of the other stat classes and have fun. So consider that if you really enjoyed the class. What was the purpose of this class? It's designed to say, if you see a scenario, what's the right way to analyze it? And if you're looking at an analysis, what are the right conclusions that you can draw from that? Okay, so we've talked about a lot of different scenarios. Let's do our map and draw them out. When you want to know what scenario you should be working with, the first question is, what am I testing? Okay. And some of this map is familiar. The final will have a lot of stuff from test 2 on it. It's going to feel a lot like test 2 was. Here's a scenario, how do you analyze it? Here's some analysis, what do you have to say? So on test 2, we talked about means and we talked about proportions. Okay? How do you know? Well, a mean is going to be numerical data. Proportion is going to be categorical data. Imagine to yourself, if you were the person doing the study, what would you be writing? If you're writing yeses and nos, we're talking proportions. If you're writing numbers, we're talking numerical data. And when I say numbers, it's a number that could be averaged. Like telephone numbers isn't going to count because you can't average telephone numbers and get something meaningful. So, numerical data, and we say how many. And when we started talking about hypothesis testing and confidence intervals and what they meant, we used one mean that we were testing, just a mu. Later, we did go into testing 2 means, and even regression counts as means. Now, it's a little different because it's like testing a mean that moves. It moves in a straight line. For each x, what is the mean? Each x, what is the mean? And we tested whether those means follow a linear trend. So regression is a moving kind of mean. So does that really count as a mean? I don't know. Some people like to draw an extra arrow coming out here for regression. And they say this is when you have numerical by numerical data. Numerical, it now looks like discriminable. That's okay, can you even see it anyway? If my head gets out of the way. This says numerical by numerical. It's an x instead of by. But the point is, if you see you have xy data, then you can jump straight into it must be regression. If we're talking about means, you could have 1 or 2. Now proportions started out the same way. How many? Okay. And we did one proportion, which acts very similar to how the mean did. And then we jumped right into 2 proportions. And with that chi-squared stuff, we talked about having many proportions. All right? The proportion for white, black, Asian, Latino, Indian, all of those different kinds of categories, lots of categories, that leads us to a chi-squared test. So is that really proportions since you're looking at so many interrelations? Well, some people draw an extra arrow out there and they say it's for categorical by categorical. So, for example, we had at the airport, what proportion of the different races are getting selected? Other categorical by categorical is, does gender depend on what color of car you drive? Categorical by categorical. And so that is going to lead us off into chi-squared. This direction is going to lead us off into regression. We are actually missing something if you notice. We have numerical by numerical, categorical by categorical. We're missing categorical by numerical. That's a time issue. That would take us to ANOVA, and we just don't have time to cover ANOVA. But it is super cool. In fact, you need to say ANOVA with respect, because ANOVA is so cool. ANOVA. I'm going to create a superhero called the ANOVAnator. I'm really going to do it someday. Can we back that up? That just sounds silly. Yeah, take that out. All right. What are we testing? We started with means. At the very beginning of class, we did one mean. But before you could test it, there was something you had to know. This fence. And the fence is, do you know that it's normal? Well, for means, if it says it's normal, that's great. But if it doesn't say it's normal, you can still analyze it if your sample's large enough. And we use the rule that n had to be greater than 30. For categorical data, saying that it's normal doesn't make sense. You're talking about categories. What does it mean to be normally distributed? So it's not going to say it's normal. But if you have a large enough sample size, the proportions will still follow the central limit theorem. And so our rule was NP had to be greater than 15, and N1 minus P had to be greater than 15. Right? Now there is still a fence when we talk about regression. But it's not just normality, there's 5 assumptions. 1, 2, 3, 4, 5. And it's not based on sample size. You can't just say 30 is a magic number. You've really got to look at those residual plots. And you're looking for, is it linear? Do we have constant variance? Okay, do we have normality? And that's normality in the residuals, and you should feel comfortable with that. We need independence, meaning it needs to be random data, independence, and the residuals need to average 0. And I realize I have reached the end of the board, and I haven't actually done any regression. I'm just talking about this fence here. We will worry about board space in a minute, because I don't know what to do with that. But for the chi-squared stuff, there's also an assumption you have to check. Okay? It's not just normality, because we're talking about lots of proportions. So we came up with a very simple rule, the most simple of rules that you'll see, and it's all the expected values have to be greater than 5. If your expected values are greater than 5, then it's okay to do the chi-squared test. So everything we do has some check. And you should expect to see on the final some question that says cannot do. All right, watch for that. There's a hint for people who actually watch through the video and the little salesman rep become a statistician. So, one mean, let's say we do know that we're okay with normality, either because our sample size was large or maybe it said so. The next question is, do we have S or a sigma? And how do you know? Well, did this S come from a sample, or did it just come from the problem, abracadabra, somehow we know it? Well, when we started talking about hypothesis tests, we claimed we knew a sigma. Why? Because it was easy. And Z equals X bar minus mu, sigma over square root of n. And that helped us be able to talk about the 7 steps of a hypothesis, what is a p-value, how does changing your alpha matter, with a very simple problem. And you could rewrite this to make a confidence interval. Do I have space on my board? Maybe. I'll give it a try. Z sigma over square root of n. Now watch for this. This is a common mistake. People will calculate this Z when they need a confidence interval and then plug that in here. If it asks for a confidence interval, you're going to get this off the table. If it asks for a hypothesis test, you're going to calculate this from your problem, okay? So these are different z's depending on whether you're doing a hypothesis test or a confidence interval. After we got done with this was chapter 5 is what my memory says, then we said, okay, let's pretend we don't know sigma. Well, then we're going to have to use S. If you use S, that tells you you're going to be doing a t-score. And you need to know degrees of freedom, which is n minus 1. Why do I write n minus 1? To remind myself that when I look at the t-table, I've got to look at the right row corresponding to degrees of freedom. And then I go x bar minus mu, S over the square root of n, and my confidence interval is very simple. Please note the similarity between these two equations, all right? On the test, you can have 2 pieces of paper for study notes. That's front and back, so 4 sides, plenty of room. You should not feel like there's so many equations you can't fit them on there. There's really one basic idea, and then you alter it depending on the scenario. So there's one mean. After that, we start talking about 2 means. And the scenarios we talked about included matched pairs. And that's going to be our first question. How do you tell if it's matched pairs? Every data point in column A matches a specific data point in column B. And you can't mix those up. If it is matched pairs, watch, I'm going to cheat because I'm low on board space. It goes back to this. Now, this isn't the way we usually write it. Often I'll put little d's on here. What's the point of the little d? It's just to remind you that you're looking at the differences, not the actual values. So little d's on here. And the mu, when we're talking about matched pairs, is going to be 0. But really, this is the equation we're working with. And that's what makes matched pairs cool. It looks like 2 samples. It acts like the 1 sample. What if it's not matched pairs? Well, then that means we're talking about the independent test. And that's going to be a t-score with a small n minus 1. Why do I say small n minus 1? Because group A is going to try to tell you what degrees of freedom are, and group B is going to try to tell you what degrees of freedom are. And fancy computers have a really cool way of getting a good degree of freedom. We're just using a simple rule, use the small degrees of freedom. And that gives us our hypothesis test, x bar 1 minus x bar 2. That's what we have instead of a single x bar. And the mu we're interested in now is 0. Yes, I'm really writing the 0 on there because I want to show you the pattern. Over. Now, when we're talking about 2 groups, we have an s over the square root of n for the first group, s over the square root of n for the second group. We want to square those into variances. So this becomes s1 squared over n1, s2 squared over n2. And we've talked a lot about that. You should feel comfortable with that. So there is our hypothesis test. I could rewrite this to make a confidence interval if I had a board that was about 1 foot longer. But I hope in your study notes that you go ahead and do that out and see that it's just like the way these guys work. Let's come over here and talk about 1 proportion. If it doesn't crash into my matched pairs. Here, we'll put it there. 1 proportion, it's a large enough sample size. That's a z-test. Proportions are always z. There is no t for proportions. It's going to be p hat, which you got from the data, minus p, the proportion you're hypothesizing, square root of p, 1 minus p over n. Now, if I'm going to write my confidence interval equation, it's going to look slightly different. Here, this is a video, right? You can back it up if you didn't get this right here. We'll just give myself some room. The confidence interval is going to look a little different because right here, instead of p1 minus p, I'm going to do p hat. Simply because p hat is going to be the best estimate I have. And according to the theory, we have a large sample size, so p hat and p should be close. So this is giving me the best error that I can get, and that gives me my confidence interval. What if we're talking about 2 proportions? Same pattern as we did here. I'm going to take a z, p hat 1 minus p hat 2, subtract 0, and square root of. Now, for the error structure, if p1 and p2 are supposed to be equal, now we want a pooled proportion. p 1 minus p, p1 minus p, and 1 and 2. These little pieces don't have square roots on them because we've squared them to turn them into variances. And this p is a pooled proportion. That was chapter 7. You should feel comfortable with that. All right? For the confidence interval, we don't know that p1 and p2 are equal anymore. So we can't do this fancy pooled trick. So for hypothesis testing, we always use a pooled p. For confidence intervals, we never do. That's going to be p hat 1 minus p hat 2 plus or minus. No, it won't fit. Yes, it will. You're squishing me. No, he's touching me. I need to go to the bathroom. Are we there yet? I need just that much more room on the board. We're going to try it. Are you ready? P1, 1 minus P1 over N1 plus, that's not fair. He got so much space. Should I write on the wall? No, look what happened last time. Do you guys remember that video? It never got cleaned up, okay? I have no idea how to clean that off. We're actually not allowed to clean our own offices. It's because they think that we're too dumb to not hurt ourselves with the cleaners. I'm not making it up. That's actually a university rule. P2, 1 minus P2 over N2, and there you can imagine that it would actually fit on the board. Okay? So this part is just like the map we did before test 2. All this should be reviewed. You could go look at the video for the map for test 2 and see all that. What do we have that's new? We've picked up some chi-squared stuff and some regression stuff. So let's make some room. Please don't erase me. No, I swear I'll squish that out. Okay. So let's talk chi-squared testing. If you have rows of categories and columns of category, what we're going to be testing is, are these categories independent of those categories, right? So dog, fish, bird, cat, and California, Wyoming, Utah, Texas. So we're seeing, does the type of animal you choose to have a relationship with what state you live in? That's an example of your test of independence. For tests of independence, you have to calculate those expected values, which makes these problems a real pain to try to do on the test. So if you need to do this kind of a thing, you'll probably see me fill in most of the expected value table, because otherwise you would spend 20 minutes of your exam on those expected values, and that would just be annoying. Expected value is calculated as the row total times the column total divided by the table total. There's way too many totals in that. But you should practice this, you know what I mean, right? The row total, column total, and the table total. That's how you calculate those expected values. And then to get the chi-squared value, you take your observed minus your expected. That's like x minus mu, or x bar minus mu. We square it for the same reason we like to square variances. And dividing by the expected value gives us an estimate of the error structure. You divide by expected values, not observed values, because these, according to the null hypothesis, are better. So if the null hypothesis is true, that's the best one to use. And that's how statistics works. We assume the null is true, and from there we build a model. Now, if it's a goodness of fit, you don't need this part, because you can calculate what the expecteds are just by reading the problem. But you still do this for your chi-squared. Now, the test of independence has degrees of freedom, row minus 1 times column minus 1. If you're talking about the goodness of fit, then your degrees of freedom are going to be k for the number of categories. Why do we use k for categories? Probably some other language to blame. German. It must be German. If you write k in categories in German, it starts with k. I don't know. It's just tradition, okay? K minus 1 for the number of categories minus 1. Now, for goodness of fit testing, it's going to look like one row. For the test of independence, you have multiple rows. So when I say k, I'm talking about how many categories are in that row. And for some reason, people seem to like the chi-squared. I'll hear a lot of students say it's actually easier than these other types of tests. And that's great. A little surprising, so many moving parts, but I guess people like seeing moving parts. Okay, let's talk regression. When we have regression, x, y, dots, line going through it, but that's not the picture we talk about for the test. We're talking about how much variability is there in the slope. Beta 1, that's what we're testing. And so it's a t-score. Degrees of freedom are going to be n minus 2 because we have a slope and an intercept, so it's minus 2 there. And we have beta hat 1, that means the beta you got out of your output from the computer. Minus 0, because that's what we thought we were going to be getting. Divided by, and here, let the computer calculate this guy, the standard error of the beta hat 1. It'll spit all that out. It'll worry about the square roots of n's and everything else. So the computer will spit that out. If you want a confidence interval, it's going to be beta hat 1 plus or minus your t-score, and minus 2 is the degrees of freedom, and standard error beta hat 1. And I'm purposely squishing all these letters together to remind you this is just a number. You don't have to square root in it. You don't have to do anything. The computer already took care of that. That's for the confidence interval. For the chi-squared, there is no confidence interval that we have talked about. Okay, so don't worry about that one. And that covers the map of what we tried to do. I would love to put the regression stuff over there and the chi-squared stuff over there, but it's not like my camera's that wide anyway, so. All right, let's do another video and we will talk about the kinds of problems you might expect to see on the exam once I get my screensaver to let me back in.